All right, welcome. This is the AP Physics multiple choice solutions for the conservation of energy. Here I'm covering questions 13 through 24. All right, so the first one here, you could read the question, but it says which is true regarding the absolute value of each work. A couple of things you would like to notice here is that the object is moving to the right. Now, that means that the force applied and there's a force applied and there's a force of friction. The force applied is greater than the force of friction. So if you want to multiply this by distance, you now get your work. So your work done by your applied force is going to be greater than your force of work done by your friction. So this needs to be true. So this can't be true. Okay, so this can't be true. Here you also want to now look at your which is regarded as true. So you want to look at your force normal and your force of gravity. A couple of things that you should have noticed is that this is a theta. So there is a here you have a sine. So you have an F sine theta part here, and which is going this way, and you have a F cosine theta part. Nope, I missed. I've this is cosine theta, right, which is going horizontal, and the vertical part is your F sine theta. Yep, that's right. Okay, so if we drew this out, you should see that the forces up is your normal force. Then also there is a force sine theta, and going down is your FG. So here you could set it up. Normal plus F sine theta is equal to FG. Okay, all we have to do is multiply this by distance. Now we get the work. So we have the work of the normal plus work of the F sine part and work done by gravity. Okay, so the work normal. So let's solve for the work normal. The work normal is equal to work of gravity minus work friction sine theta. So it seems like the force normal, if we want to compare it to the force gravity, okay, is smaller. Okay, why? Here it is it mathematically, but you could also understand. So let me paint you a picture. So normally before the force normal, let's say it was 5, right? Newtons. And the force of gravity was also going to be 5 newtons, all right? So now you see how there's an other F sine theta part. So if there's a sine theta part, that means this is like 4 newtons, and the F sine theta part is taking up 1 more newtons, right? Because again, it still needs to balance. So the force normal is a lower amount because there's another force taking up part of that force. So overall, if you just look at force normal and force gravity, you can tell that force normal has to be smaller than force of gravity. Again, you can think about it work if you just multiply by the distance. Okay. Next, here you could see what's happening here, but which is correct about the work of the force, blah blah blah. Again, you could treat this as all as a force problem. All you have to do is just multiply this by distance d, like what it says here. So it just becomes work. Okay, work normal, which is true. Which equation is correct? Work normal is equal to 0. This is wrong. Work normal is going to be equal to the work of force of gravity. Not work done by gravity. Okay. Work of gravity is mgd. Not quite, because again, d is the horizontal. So work gravity is actually mgh, where h is the height. So that's wrong. This is correct in the sense that work work of the force is FD cosine theta, because this part that is happening is your cosine theta part. And again, this is your horizontal line. So this is correct. And the other one is force of friction. Just multiply that by D will get you the work. So this is also correct. Okay. Some Let's go to 15 now. A 10 kilogram mass travels at a uniform 5 meters per second in a circle at a radius 2 meters. What work is done on the mass? What is done on the mass? That's zero. That makes no sense. It's a trick question. Work done on the mass. It's zero. So there's work done by the mass, but there's no work done on the mass. Okay. Um, so let me just draw you what's happening. So here we could have the radius of the circle, and this is the string. Here is your 10 kilogram, and it is moving at a velocity of 5, and the radius here is 2 meters. Okay, what is the work done on the mass? Well, that wouldn't, so we know that work is equal to distance times cosine uh, force times um, distance times cosine theta. Okay. Here you could also grab the same information, but this is the work done by the object. By the object. So this is work done on the object. So it would be zero. Okay, because the mass, because there's nothing interacting with the mass here. There's no work moving on the mass. Okay. Next, this is a definition part. A kilowatt hour is a unit of what? Please understand work has this is just work is equal force times distance. There is no time here. So this is off. And so what you have here is a kilowatt per hour. Right? So let me just give you um, the definition. A kilowatt per hour is a unit of power. Okay? It's a unit of power. Okay, so kilowatt, this is work done by an electrical current. Okay, and this is your time. So this is once you have the work times your power. Work times time will get you power. Okay. And 17. Let's say you lift an object 1 meter. If you push it, blah, blah, blah. Compare. Oh, you're comparing it. Okay. First of all, you want to take a look. What is this? If it's the height here is 1 meter. And let's see, push an object, which 30 degrees, which takes you twice as long as it compared to lift. So, that's interesting. Did you know here the MGH is just what's the mass? You could just like well, let's just make the mass 10. Gravity is 10. Height is 1, so we could say this is 100, right? Here we could say it's the same height, right? It's the same height. So same mass, 10 MGH, just 10. Gravity is 10. Height is 1. So it seems like their potential energy, okay, is being the same, and we know that the work done lifting up is equal to just mgh, right? Because it's all being converted to potential energy. So um, they say they have the same amount of work, first of all. So it's this one's wrong, this one's wrong. Now, but here's the issue. This one takes twice as long. This one takes twice. Takes twice as long. Okay? Alright? So, the fact that it takes twice as long, the fact that it takes twice as long, okay, it means that the power, so here, let's say, we could even grab the power. Okay, power is like 100, and let's say this one took like 1 minute. Okay, but here it takes twice as long, so it's 100 divided by 2 minutes. So do you see how it's the power is less? So that would be correct. It's the same amount of work, 100 100, but the second one requires less power. Okay, because again, why? Because it's taking twice as long. All right, good, 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 good. Next, this is a spring hanging, and we know by default that this is Hooke's law. Okay, the restorative force is equal to minus kx, and we know the minus is just a direction component. So I would say that if this is 0, okay, this, what is pushing it forward, is your F restorative force. Here would be a minus F restorative force. Okay, but again, these are all magnitudes. All right. So it seems like here they have the same distance. So here you could say this has a negative 5 because this can be 0. So this is going to be 5. Okay, I could just throw some units here. 5 meters, 0 meters. Uh, okay, negative 5 meters. All right, the magnitude of acceleration is least at where? So you want to look at its least acceleration. Okay, we know that we know that there are accelerations here and accelerations here, but if you want to look at the least, it's probably at equilibrium. So it's going to be 2. Why? Because at equilibrium, the F is going to be equal to negative k times 0, which is just 0. So there is no acceleration. The potential energy is greatest at, that would be 1 and 2, because again it has the same distance. So the restorative force up here is negative k5, and the other one, which is at negative 5, which is also going to be at 5k. So both of these have a restorative force of 5k. So which one has the same amount? The potential energy is greatest where? Well, it would be both because it both has 5k. The magnitude of the restorative force is the same. Okay, that's also the same because here's the force. Okay, the potential energy is greatest at what point? Huh, that's a trick. You can make the art. Okay, so I know the answer definitely is D here, but the question about the potential energy is very interesting here. 19 might be a trick question. If I assume this to be true, like I make this 0 and this is minus, this has to be a minus and this is a positive. The potential energy is defined as U is, let me just change its color. U is equal to mgh, right? So mass gravity is the same height is different. No, they have the same height. Mm, no. The fact that they have the same restorative force, they should have the same amount of potential energy. This is my okay. This is my logic. All the force is all the energy force is in the restorative force. All the force has to be converted into quote unquote the energy. That's why I think it's the same, and that might make sense. Hmm. Yep. So yep, these answers are correct. All the forces should be translated into the potential energy. Okay. If someone could argue differently, let me know. But so far, I know that they both have to be the same. Hooke's law for 20 is the explanation, and 19, my thought process is that all the energy in all the forces in Hooke's law is translated into the mgh. Okay. And here we have, okay, 21. 21, it's something that you just would have to memorize, and I already have a picture for you. It's this. Okay. This is what you need to remember. Okay. This is just the way things are. And this is for a oscillation. Okay, this is for an oscillation. Okay, all right. So here you have the potential energy is in red, and the potential energy when it is away. Okay, uh, it has a lot. Then when it comes to zero, it's when it approaches zero, it becomes uh, nothing. And then when it goes up, it has high potential energy. Okay, so let me see what I mean by this. So here, what I mean by this is imagine a pendulum. Okay, this is basically when it is at zero. This is when it's at negative a, and this one has positive a. Do you see how it has potential energy? Potential energy swings all the way here, gets you zero, then it swings back, negative energy. Okay, but you see how it has potential energy on both sides? That's what it's referring to. Vice versa. Okay, the kinetic energy basically is opposite to that. So here, the fact that it has all potential energy here, this is when he has all. This is his when he has all P, no K. Here, this is when it has all. Mm, we use PE for potential energy, but we used the letter U in class. So this is all U and no K here. Okay. You see how this is like the if you think about it, like a ramp. Okay. You see here, this is when it's at A, and this is when it's at negative A. Okay. All potential energy, no kinetic. Now, once it reaches here, okay, this is all K, no U. So this is what it means here when it's at zero. This is all K, no U. Okay, so which is the kinetic energy one? Okay, we know it has to be what starts from zero, so it would be B. Okay, it looks like this. This is your kinetic energy. Okay, starts from zero, gains so much kinetic energy when it reaches the center or the zero part. And then it loses all the part as it swings back out. Potential energy is its inverse. Okay, and the total is up here. This is the total. Okay, this is the total. Um, this is your kinetic. This is your potential energy. Okay. But this is very interesting to note right here. These are when potential energy and kinetic energy are the same. So equivalent to that, you're probably looking at like somewhere right here. This is where PE is also equal to KE. PE is equal to KE. So it's somewhere in the middle. Okay, somewhere in the middle. Right? And is that it? Or do we have one more question? Oh, one more question. Okay, so you have a fuel burn that is occurring. If the certain point the mass of the rocket is half, its original mass and velocity is twice, how are the momentums and energy affected? Okay, so let's see if I wrote any equations for this. Yeah, okay, sweet. So, if a certain point the rocket, the mass of the rocket is half its original mass, and velocity is twice the original velocity. How is momentum and energy goes energy affected? Okay, so 24. All right, so here 24. Okay, let's see. All right, so let's take a look at the equations. Okay. All right, so we have um, the new mass is gonna be half, right? So that's the new mass. The new mass is gonna be a half, and the new velocity is gonna be what, twice? All right. So we want to look at its momentum. So let's take a look at momentum. All right, momentum is just defined as um, mv. Okay. So let's just throw it in here. So the new mass is a half. So that's what we said the new mass is, and the velocity is twice the velocity. Okay, so 1/2 times 2, these cancel out. All you have is mass and velocity. So from here to here, so this was your change. It seems like nothing happened to the momentum. Okay, now, oops, sorry. Now let's take a look here at your kinetic energy. And we know kinetic energy is 1/2 mv squared. Okay. And we know that mass is 1/2, so this is 1/2 m. Velocity is 2 velocity squared. Okay. So it becomes a half times m. This becomes 4, 2 squared, and v squared. So a half times a half becomes 1/4 m. 2 squared is 4, and we have a v squared. We have 1/4 and a 4 here. Mass velocity squared. Alright, so it seems from here to here, it basically doubled. Okay, so it would be C, kinetic B. Momentum is unchanged and kinetic energy is doubled. Okay. Yep, and that's it. Those are all your solutions.